In this video, we're going to focus on Coulomb's law. We're also going to work on some problems associated with it. But before we do that, let's begin our discussion with the atom. Now, at the center of an atom, you have the nucleus. And inside the nucleus of an atom, there are subatomic particles known as protons and neutrons. Neutrons are neutral in charge. Protons carry a positive charge, whereas electrons, which orbit the nucleus, they carry negative charges. One proton has a charge of 1.6 times 10 to the negative 19 coulombs. Since we don't have fractional protons, electric charge is said to be quantized. It exists in discrete amounts. So this is the fundamental value of charge. So electric charge will always be a multiple of this number. Now, an electron has the same magnitude of charge, but with a negative sign. So the charge of an electron is negative 1.6 times 10 to the negative 19 coulombs. Now let's place a positive charge next to a negative charge. What's going to happen if we put these two charges next to each other? Let's call the first charge Q1 and the second charge Q2. What you need to know is that opposite charges attract. Like charges repel. So because these two charges are opposite in sign, they're going to attract each other. Q1 is going to feel a force that will basically propel it towards Q2. And Q2 will also feel the same force. These two forces are equal in magnitude, but opposite in direction. Now, the equation that helps us to calculate that force, also known as an electric force, is Coulomb's law. The electric force is equal to the proportionality constant K times the magnitude of Q1 times Q2 divided by R squared. Now, R is the distance between the center of these two charges. Now, these charges are known as point charges, where the size of the charge is irrelevant. The proportionality constant K is equal to 9 times 10 to the 9 newtons over square meters times square coulombs. So make sure you know this value because we're going to use it when we're solving problems. Now this proportionality constant is always equal to, it's also equal to 1 over 4 pi times epsilon naught. And epsilon in this problem, or in this situation, is equal to 8.85 times 10 to the negative 12 coulombs squared over newtons times square meters. So this is the permittivity of free space. Now, when solving problems associated with Coulomb's law, K is the value that you're going to use most often. Now, we said that opposite charges attract. Let's draw a picture with two like charges. So if we were to put a positive charge next to another positive charge, these two charges will repel. So they will feel a force that will push them apart. But these two forces are equal in magnitude, but opposite in direction. So now to review, remember protons carry a positive charge and electrons, they carry a negative charge. Now whenever you have an object that has a net positive charge, you need to be aware that what it means is that there's more protons than electrons in that object. If you have an object that is negatively charged, that means that it has more electrons than protons. So whenever the number of protons and electrons are equal, the object will be neutral in charge. But if you have more protons than electrons, the object will carry a positive charge. If there are more electrons than protons, then it's going to have a negative charge. Now let's go back to Coulomb's law. This equation describes the relationship between the electric force, the magnitude of the charges, and the distance between the two charges. If we were to increase the magnitude of one of the charges, the electric force will increase. So let's say this is Q1 and this is, let's put a positive charge, and let's say Q2 also has a positive charge. And let's say the force acting on each of them is 100 newtons. Now, what do you think is going to happen if we increase the magnitude of one of those charges? Let's say we double the value of Q2, so it's 2 times Q2. Well, since we increase the magnitude of the charge, the electric force is going to increase in value. It's going to double. It's going to become 200 newtons. So if you double the magnitude of one of the charges, the force will double. Now let's say this is R. What happens if we place Q2 further away from Q1? So let's say if we double the distance between Q1 and Q2. So this is going to be 2R instead of 1R. What's going to happen to the force? Notice that R is on the bottom of the fraction. If you were to increase the distance between the two charges, the magnitude of the force will decrease. The force is inversely related to the square of the distance. So the force is not going to cut in half. It's going to be 1/4 of its original value. Because if you were to plug in 2 into that equation and 1 for everything else, it would be 1 over 2 squared, which is 1 over 4. So it's going to be 1/4 of its original value, which means it's going to be 25 newtons. So if you were to double the magnitude of one of the charges, the force will double. If you were to double the distance between the two charges, the force will be reduced by a factor of 4. So the electric force is strongest when the charges are placed closer together, or if you increase the magnitude of the charges. Now let's talk about the units associated with Coulomb's law. The unit of force is the Newton. Now for Q1 or Q2, which represents the electric charge, the unit for that is coulombs. 1 coulomb is a large amount of charge. So typically you'll see the charge represented in microcoulombs. 1 microcoulomb is 1 times 10 to the minus 6 coulombs. 1 millicoulomb is 1 times 10 to the negative 3 coulombs. And 1 nanocoulomb is 1 times 10 to the negative 9 coulombs. Now R, the distance between the charges, needs to be in meters. Sometimes you'll see values in centimeters or millimeter. So remember, 1 centimeter is 1 times 10 to the minus 2 meters. And 1 millimeter is 1 times 10 to the minus 3 meters. You could also see it this way. 1 meter is equivalent to 100 centimeters, and 1 meter is equivalent to 1,000 millimeters. So those are some other things that you want to know when dealing with problems associated with Coulomb's law. Now let's work on some practice problems. Let's start with this one. A 10 microcoulomb point charge is 25 centimeters away from a negative 20 microcoulomb point charge. Calculate the magnitude of the electric force between them. So let's begin by drawing a picture. So we have two charges. One is positive, the other is negative. We'll call this Q1 and Q2. So Q1 has a magnitude of positive 10 microcoulombs. Q2 has a magnitude of negative 20 microcoulombs. And the distance between the two charges is 25 centimeters. So now let's calculate the force acting on the two charges. Now keep in mind, since we're dealing with opposite charges, these two will feel a force of attraction. So these two forces will be equal in magnitude. The force that is acting on charge 1 due to charge 2, you can call it F1, 2. The force that is acting on charge 2 due to charge 1, you can call it F2, 1. But for this problem, they're exactly the same. Now, the proportionality constant K is 9 times 10 to the 9. Q1 is 10 microcoulombs. So to plug this in, replace microcoulombs with 10 to the negative 6 coulombs. Q2 is negative 20 microcoulombs. Now for this formula, you don't need to worry about the negative sign because we already know the direction of the force. Also, we only want the magnitude of the electric force. Electric force is a vector. It has both magnitude and direction, but since we only want the magnitude, we don't need to be concerned with the direction, and we don't need to worry about the negative sign. So we're going to plug in positive 20 times 10 to the minus 6 coulombs for Q2. Now R, the distance between the two charges, is in centimeters. We need to convert that to meters. Well, actually, you can simply plug it in like this. 25 centimeters, you can write it as 25 times 10 to the minus 2 meters. You can replace centi with 10 to the negative 2. But if you wanted to convert it, here's what you could do. You can multiply 25 centimeters by 1 meter over 100 centimeters. And this will give you 0.25 meters when you divide 25 by 100. Or you can move the decimal point 2 units to the left. That will give you 0.25 meters, which is the same as 25 times 10 to the negative 2. So let's go ahead and plug everything in. 9 times 10 to the 9 times 10 times 10 to the minus 6 times the other number divided by, and for this part you want to put it in parentheses. You can divide it by 0.25 squared if you want to, or type in exactly what you see here. So the answer that you should get is 28.8 newtons. So that is the magnitude of the electric force that is acting on both of the two charges. Now let's move on to number 2. The electric force between 2 point charges with a magnitude of 800 nanocoulombs and 900 nanocoulombs is 15 newtons. How far apart are the two charges from each other in centimeters? So we can draw another picture if we want to. So here's the first charge and here's the second charge. Both of the two charges are positive. We need to calculate the distance between them. And we know the force acting on each of them. Now because these two have the same charges, they will repel each other with a force of 15 newtons. But how can we calculate R? Well, let's start with Coulomb's law. F is equal to K Q1 over Q2. K Q1 times Q2 over R squared. So what we're going to do is we're going to isolate R in this equation. So to do that, let's multiply both sides by R squared first. So these will cancel. And we're going to get F times R squared is equal to K Q1 Q2. Now let's divide both sides by F. So this will give us R squared is equal to K Q1 Q2 over F. Now to get R by itself, we need to take the square root of both sides. So this is the formula that we could use to calculate the radius, or not really the radius, but I think of the radius when I see R, but the distance between the two charges. So R is going to equal the square root of K Q1 times Q2 divided by F. So K is 9 times 10 to the 9. Q1, it really doesn't matter which one is Q1, so let's just make this one Q1 and the other one Q2. Q1 is 800 nanocoulombs. Keep in mind, nano is 10 to the minus 9. Q2 is 900 nanocoulombs, so 900 times 10 to the minus 9. And then F is 15 newtons. Now for those of you who want to see the units, K, I'm going to plug in the units in this formula. K has the units newtons over square meters, square coulombs. Q1 is in coulombs, Q2 is in coulombs, F is in newtons. So the unit newtons cancel, the unit coulombs cancels. So we have square meters, and when you take the square root of square meters, you're going to get the answer in meters. For those of you who want to see how the units work in that formula. Now let's go ahead and plug in these values into a calculator so we can get our final answer. So let's plug in the square root of 9 times 10 to the 9 times 800 times 10 to the negative 9 times 900 times 10 to the minus 9 divided by 15. So you should get this answer, 0.02078 meters. Now let's go ahead and convert that to centimeters, because we want the answer to be in centimeters. Now remember, 1 meter is equivalent to 100 centimeters. So you want to set up the conversion in such a way that the unit meters cancel. So we're going to multiply 0.02078 by 100, or simply move the decimal 2 units to the right. So we're going to get 2.078 centimeters. So that's the distance between the 2 point charges. Number 3, a force of 500 newtons exists between 2 identical point charges separated by a distance of 40 centimeters. Calculate the magnitude of the 2 point charges. So let's draw a picture. So here are the 2 point charges. They're identical. They can both be positive or both be negative. Now, because they're identical, we don't have to describe them as Q1 and Q2. We can simply refer to them as Q because they're the same. As the problem mentions, they are identical. Now we know the distance between the 2 point charges, and so that is our R value, which is 40 centimeters. Now we want to convert that to meters. So to quickly convert centimeters to meters, simply divide by 100 or move the decimal 2 units to the left. So 40 centimeters is equivalent to 0.40 or 0.4 meters. Now we have the magnitude of the force that repels these 2 charges away from each other. That's 500 newtons. How can we calculate Q? Well, let's begin by writing the formula. F is equal to K. Now typically we would write Q1 and Q2, but we're going to replace Q1 with Q and Q2 with Q. So Q times Q is Q squared. Now what we need to do is we need to isolate Q squared. So I'm going to multiply both sides by R squared over K. The reason why I want to multiply both sides of the equation by R squared over K is so that on the right we could cancel R squared and we can also cancel K. So what we have left over on the right side, which is now on the left side because I reversed it, is Q squared. Q squared is equal to F times R squared over K. Now to get Q, we need to take the square root of both sides. So for this particular problem, because the 2 charges are identical, we can calculate Q using this formula. It's going to be equal to the force times the square of the distance divided by K. So the force is 500 newtons. R is 0.4 meters. And then K is 9 times 10 to the 9 with the units newtons times square meters over square coulombs. So we can see the unit newtons will cancel and the unit square meters will cancel. And so we're going to be left behind with square coulombs. But when we take the square root of that, the unit will just be in coulombs. So let's go ahead and plug this in. So it's the square root of 500 times 0.4 squared divided by 9 times 10 to the 9, all within the square root symbol. So you should get 9.428 times 10 to the negative 5 coulombs. Now to get the answer in microcoulombs, take this value and divide it by 10 to the negative 6, or 1 times 10 to the minus 6. So if you do that, you should get 94.28 microcoulombs. So that is the magnitude of the two identical charges. Now let's move on to number 4. How many electrons represent a charge of negative 70 microcoulombs? What we can do is we can convert this to the number of electrons. First, let's convert it to coulombs. We know 1 microcoulomb is 1 times 10 to the negative 6 coulombs. So we can cancel the unit microcoulombs. Now we have the conversion factor between number of electrons and electric charge. Keep in mind, 1 electron has an electric charge of negative 1.6 times 10 to the negative 19 coulombs. It's really negative 1.602, but if you round it to negative 1.6, your answer will still be accurate. So let's put coulombs on the bottom and then 1 electron on top. So now we can cancel the unit coulombs. So it's going to be negative 70 times 1 times 10 to negative 6 divided by negative 1.6 times 10 to negative 19. So the answer is 4.375 times 10 to the 14 electrons. So that's how many electrons are represented by a charge of negative 70 microcoulombs. Now what about number 5? What is the electric charge in microcoulombs of 5 times 10 to the 14 protons? So for this problem, we're going backwards. We're converting number of protons to electric charge. So let's start with what we're given. 5 times 10 to the 14 protons. Now let's convert protons to charge. We know that 1 proton has a charge of positive 1.6 times 10 to the 19 coulombs. And we know that 1 microcoulomb is 1 times 10 to the negative 6 coulombs. So the number of protons cancels and the charge in coulombs cancel. So we get the charge in microcoulombs. So it's going to be, oh, by the way, this is negative 19. So it's 5 times 10 to the 14 times 1.6 times 10 to the negative 19, and then take that result divided by 1 times 10 to the negative 6. And you should get 80. So the charge that it represents is positive 80 microcoulombs. So that's the answer for number 5. Number 6, a metal sphere has 4.3 times 10 to the 21 protons and 6.8 times 10 to the 21 electrons. What is the net electric charge on this metal sphere? In order to determine the net electric charge, we need to know if we have more protons than electrons, or vice versa. In this case, we have more electrons. What we really need to do is determine the excess number of electrons and convert that to electric charge. But there's a simple formula that you could use to get this answer quickly. So the net charge Q, let me draw that better, is going to be the difference between the number of protons and electrons. So if we get more protons than electrons, this number will be positive. If the number of electrons exceeds the protons, this number will be negative. So it's going to be P minus E times the charge of a proton, which is 1.6 times 10 to the negative 19 coulombs. So for this problem, all we need to do is plug in these values. So we have 4.3 times 10 to the 21 protons, and we have 6.8 times 10 to the 21 electrons. So 4.3 minus 6.8, that's a difference of negative 2.5. So because it's negative, that tells us that the overall charge will be negative, and so that means that we have more electrons than protons. So negative 2.5 times 10 to the 21 times 1.6 times 10 to the negative 19. This is equal to negative 400 coulombs. So that is the net electric charge on this particular metal sphere. A 100 microcoulomb charge is placed at the origin. A negative 50 microcoulomb charge is placed at x equals 2 meters relative to the origin, and a 200 microcoulomb charge is placed at x equals negative 4 meters. What is the net electric force acting on the 100 microcoulomb charge? So if you want to try this problem, feel free and pause the video to see if you can get the right answer. So go ahead and work on this problem. Now the first thing we need to do is draw a picture. So we have a positive charge placed at the origin, and that's the 100 microcoulomb charge. And then at a position of 2 meters relative to the origin, we have a negative charge with a magnitude of negative 50 microcoulombs. And then on the left side at negative 4 meters, we have a positive charge with a magnitude of 200 microcoulombs. So the distance between these two charges is 4 meters, and between the two charges on the right, it's 2 meters. Let's call this Q1, Q2, and Q3. So how can we use this information to determine the net electric force acting on the middle charge? First, we need to identify all the forces acting on the middle charge. So Q2 feels a force of attraction with Q3. Q2 is attracted to Q3. So there's going to be a force that's going to accelerate Q2 towards Q3. And we're going to call that force F2, 3. So this is the force on 2 due to charge 3. Now Q2 with its positive charge is repelled by Q1. So Q2 wants to move away from Q1. So there's another force acting on Q2, and that's going to be F2, 1. That is the force acting on charge 2 due to charge 1. And so the net force is going to be the sum of these two forces. Anytime you have two vectors that are parallel to each other, to find the sum of those vectors, you can simply add them. So the net force is going to be F1 on 2 rather, plus F3 on 2, or the force exerted on 2 by a charge 3. So we just got to add those two values. So first we need to calculate each one. So let's calculate F2, 1. So it's going to be K times Q1 times Q2 divided by R squared, where R is the distance between Q1 and Q2. So K is 9 times 10 to the 9. Q1 is 200 microcoulombs, or 200 times 10 to the minus 6. And Q2 is 100 times 10 to the negative 6, divided by R squared, or 4 squared. So go ahead and type that in. So the force exerted on charge 2 by charge 1 is 11.25 newtons. So let's save that answer. We're going to use it later. Now we need to calculate the force exerted on charge 2 by charge 3. So that's going to be K Q2 times Q3 over R squared. So K is a constant. It's not going to change. It's 9 times 10 to the 9. Q2 is 100 times 10 to the minus 6. And Q3 is 50 times 10 to the negative 6. Don't worry about the negative sign. These two forces are positive because they're both directed along the positive x direction. So you can adjust the sign based on the direction of the force. Now R, the distance between Q2 and Q3, is 2 meters. So we're going to divide it by 2 squared. It turns out that F2, 3 is equal to the same number, 11.25 newtons, purely by coincidence. So now we can calculate the net force acting on charge 2. So as we said before, the net force is simply the sum of these two forces because they're going in the same direction. So it's F2, 1 plus F2, 3. And so that's going to be 11.25 plus 11.25, which adds up to 22.5 newtons. And so that's the answer for part A. Now let's move on to the next part. What is the net electric force acting on the 200 microcoulomb charge? So that's on Q1. So let's see what effect Q2 has on Q1. Q2 repels Q1. So Q2 will cause Q1 to go in this direction. So we can call that F1, 2. That's the force exerted on charge 1 by charge 2. Now Q1 is attracted to Q3 because opposites attract. So we have another force, which we'll call F1, 3. That's the force exerted on charge 1 as a result of charge 3. Now these two forces are competing with each other. Now this force is in a positive x direction, so we're going to give it a positive number. This force is in a negative direction. So the net force is going to be the sum of these two values. If the net force is positive, that means that F103 is greater, which is probably not because it's so far away. If the net force is negative, which is probably going to be the case, that means that this force is greater. So let's calculate the values of each of these two forces. Now it's important to understand that F1, 2 is equal to F2, 1 in magnitude. They have the same magnitude, but the direction may not be the same. So the sign might be different. So technically, we should say that the absolute value of F1, 2 is equal to the absolute value of F2, 1, because one might be negative and the other might be positive. So we don't need to calculate this value because we already have it here. We do, however, need to calculate this value because we don't have that yet. So F1, 3, that's going to equal K Q1 Q3 divided by R squared. Now K is 9 times 10 to the 9. Q1 is 200 times 10 to the minus 6. Q3 is 50 times 10 to the minus 6. And the distance between Q1 and Q3 is 4 plus 2, or 6 meters. So this is going to be 6 squared on the bottom. And so the force is going to be very small. So I'm going to write it over here. It's only 2.5 newtons. Because the charges are so far away, the magnitude of the force will be greatly reduced. So now we can calculate the net force. It's going to be F1, 2 plus F1, 3. Now this force is negative because it's in a negative x direction. And it has the same magnitude as that one. So it's going to be negative 11.25. And this force is positive. It's directed in the positive x direction. So that's positive 2.5. And so the net force is negative 8.75 newtons along the negative x direction. So that's the net force acting on charge 1.